go. All right, cool. So what time is it? Yep, it's 4:01, so it's time. All right, so the first thing is to figure out when our final exam is going to be on. It is in the syllabus, okay? But in case you don't know where to find the final exam time, so you go to the final exam time schedule of the ARC, website. This class meets on Mondays and Wednesdays, and the start time of the lecture. This is a lecture-only class, so we don't have a lab component anyway. Is between 2:45 and 4:25. So our final exam is going to be on the 19th of December, and the exam time is from 3 p.m. to 5 p.m. So keep that in mind, because if you come here at 4 o'clock, you have just lost 1 hour of a 2-hour exam. Okay? So make sure you remember the exam time is not exactly the same as our lecture time. Yep.
Just to confirm, that is in this room.
It is in this room. Yep. And that is in Pacific Standard Time. So is that okay? All right. So the final exam is going to be open book, open notes. As you study the material for the final exam, you probably want to start to write down some notes so you can bring that with you. The scope of the exam, the final exam, unfortunately has to cover more material this semester because we lost our second exam. So that means you have to study a little bit more compared to previous semesters, and that's kind of I have to make up for the lost time by not having exam two. Are there any questions regarding the final exam? I will give you guys a practice exam on this. Let's see. Next Tuesday would be a good time to do it. Next Wednesday, sorry. So next Monday. So on next Monday, okay, I got my dates all messed up. So next Monday is going to be the practice exam because today is Wednesday. So if I do the practice exam on next Monday, that will leave us one more class meeting, one more lecture before the final exam week starts. So if you have any questions, as you study, you might want to write that down and bring those questions on either next Monday, where we have our practice exam, or next Wednesday when we have basically a review session to help kind of go back in time and figure out what we have taught so far, especially after the first exam. And if you have any concepts that you want to clarify, next Wednesday would be the perfect opportunity to do that. So do we have any questions about the final exam, when it is, where it is? Okay, no questions. Yep. It is 53% of your final grade, as opposed to the original 40%. So it's good and bad at the same time. It's really hard to say whether a higher percentage of the final exam is a good or not. It depends on how you do in that particular exam. So I can't really assess. Is that a better thing for you to do? I can't tell. So given that, are there any other questions? Yep. Not excluding things already covered in exam one. But things that we talk about after exam one, I'm gonna have to include some of that. So is that good so far? Yep.
Is it getting longer than usual because of the extra content?
No, it's not going to be any longer. Having the duration of the exam longer than 2 hours is not going to help. Because most people will run out of energy, by the time by the end of the 2 hours anyway. Yep.
So the final material will go up to the end of today's lecture.
It will go up to the end of today's lecture. That is correct. Yep. So it will include what we talked about last time, the big O, big theta, big omega notation. And then what we talk about today, it's probably not going to be as heavy duty compared to Monday. So we probably will not get to the master theorem today. So that's probably a good thing, because I don't want to rush too much stuff at the very end. But at the same time, having some exposure would be good. So at the end of today's lecture, I will kind of let you guys know for sure what is the upper bound of the exam material. I'll give you the big O. But the big omega is after exam 1. All right, so I was messing around a little bit with my server, and so you guys might find that certain things don't look right, like within the past 24 hours or so. If you go to the website, certain things may not look right. That's because I was asking my website to automatically redirect HTTP traffic to HTTPS, and apparently that kind of messes up the CSS part of stuff. But I fixed it already, so I'm not redirecting automatically, so things should kind of return back to normal at this point. All right, and today I remember to bring my clip-on glasses, so it's actually a lot easier to see my screen, even though it looks kind of funny, but to me it's very practical because I can actually see what is on my screen. All right, so let's do a quick review of what we did on Monday and some of the terms that we encountered on Monday. So we talked about these specific terms. So the big O, big omega, big theta, little o, and little omega notations, they all have to do with asymptotic characteristics. In other words, we're not concerned about how long it takes to sort an array of 5 elements, or even 10 elements, or even 100 elements. We are talking about as the number of elements in an array increases, how does that change the amount of time it takes to execute the algorithm? And we want to look at really, really big numbers. Okay, so that's why we are looking at the asymptotic characteristics. And then on top of that, we don't need the exact value, because to get to the exact value, a lot of things have to be taken into consideration. Okay, how big of a cache do you have? Okay, if you run it on a processor with 2 megabytes of cache, the timing can be changed compared to running it on a processor that has 4 megabytes of cache. Okay, if your processor is capable of multi-threading, it might change the time constants as well. So we don't want to deal with that. Okay, that's too much detail that is not really of big consequence to us. So what we really want to do is to look at the approximation of the actual amount of time it takes to execute an algorithm. And for the most part, we don't care about the exact amount of time. We just need to know what does it look like as a curve. Okay. So then we talked about supremum and infimum. So supremum is kind of like an upper bound, and infimum is a lower bound. So we talked about the mathematical notation of how those two terms are defined. So supremum is SUP, and then you have a set notation, or you supply a set, and it will find the upper bound of that set. Infimum is kind of the same thing. INF is the abbreviation. You apply that to a set, and it is supposed to give you a, not give you A, but it will give you the lower bound of that particular set. So a limit of a sequence is the usual way that you define a limit, which is what you learned in pre-calc. Okay, we're taking the limit, and it has to converge to a single value. So if you have a function that keeps fluctuating, then it has no specific, it doesn't approach a particular value. So the limit does not exist. Okay, according to the definition of the limit, it doesn't exist. So then we talk about limit superior, which is the infimum of a set of supremums. So it's kind of the lower bound of a whole bunch of upper bounds. And the upper bounds are basically, they are different in the sense of the first one is starting from the first element of the series, of the sequence, and all the way up to the end, or the infinite, up to the entire sequence. The second one is from the second element of the sequence and all the way up. The third one is from the third element and all the way up. So that's how we make the individual supremums into a set. And then within that set, we want to take the infimum, so that's why it is the lower bound of the upper bound. And then we talk about limit inferior, which is kind of the opposite. It is the upper bound of lower bounds. So by looking at the lower bound of the upper bounds and then the upper bound of the lower bounds, what we end up with is an envelope. Okay, we're looking at an envelope that basically describes a particular sequence as the sequence goes to infinity and beyond. Okay, Toy Story. So using all of these terms, so up to section 3.5, those are only defining the terms that we actually need to express what we really want to talk about, which is the big O notation, otherwise known as the upper bound. During a little discussion earlier in my office, we kind of, me and one of your classmates talked about how we actually use big O in the wrong context these days. So when we ask, okay, so next time when you go into your cisp440 class, ask your professor, okay, what is the big O of blah, 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 okay? And then you can ask a trick question. So let's say you're asking about the time complexity of, say, bubble sort, okay, which we know is big O. Big O n squared is legitimate, okay, or n squared is a upper bound of the execution time of the time complexity of bubble sort, okay? So ask this question, okay, and ask, so is big O n cubed applicable to the time complexity of bubble sort? What do you think? Now, before you ask the question, you better have the right answer, right? Well, since it's Raj, maybe not. But is it Raj teaching 430? Okay. So what is the answer? Is n squared, which is the actual time complexity of bubble sort, an element of big O of n cubed? Yep.
Maybe a subset, not an element.
It's an element because f of n, we are asking whether a particular function, in this case n squared, by itself, is an element of big O of n cubed. It is. Very good. Because n cubed is a gross overestimate of n squared. So it actually applies. We can literally say that the big O of bubble sort can be n cubed, or n to the power fourth, or n factorial, because all of those are gross overestimates of the actual amount of time that bubble sort needs. And big O really is just asking, is this a upper bound of that? If that is the case, then big O applies. Yep.
Let's say lower than n squared. Is it impossible or underestimate?
Say that one more time.
If the big O of
Uh-huh.
bubble sort
Uh-huh.
lower than n squared, let's say like n,
Okay.
is it underestimate or impossible case?
So are you asking whether the actual bubble sort algorithm, if you ask the question, is big O of n applicable to bubble sort, then the answer is false. It is not. So if you look at f of n as the actual amount of time for a particular algorithm to complete, for bubble sort to complete, then f of n is not an element of big O of n. Okay, so maybe it helps to kind of write what we just talked about, because without actually writing it down, maybe it's a little bit difficult to visualize what I was saying. So we'll use Zernal. Okay. So what we'll do is we're going to say this. So we'll say f of n is the actual time or amount of time, AMT of time, to execute bubble sort. Okay? On a particular computer. with a particular configuration. So take your pick, just have a specification of the computer, how much RAM, what kind of processor, and this is the exact time, okay? So f of n is the exact function. So it's not going to be a very simple function because you have to take into consideration, caching, DDR behavior, the width of your memory bus, and a whole bunch of other stuff. So it changes all the little things, it changes the coefficients, but it doesn't really change the actual overall time complexity. So now the question is f of n an element of big O of n squared? And the answer is yes, okay? This is true. In other words, n squared as a function is an overbound of this f of n. Okay? So we have a very mathematical kind of obscure definition of what is the big O notation, but in this discussion we'll just use the concept and not refer to the mathematical equation. Or in this case, it's an inequality because it has to be less than infinity. The ratio has to be less than infinity. So the next question, the trick question that you might want to present to Iraj is f of n an element of big O of n cubed? The answer is yep, that is true as well. Because if n squared is already an upper bound of f of n, then n cubed is automatically an upper bound of f of n as well. Is that okay? Log of n obviously would not be, okay? Even n times log of n would not be. But, any power of n, above, 2 or more, 2 is going to count as an upper bound. So now the next question, which was what you asked a little bit earlier, is what about this question? Is f of n an element of big O of just n? Then the answer is false. It does not meet the requirement that it takes to be a big O. So it's a true-false kind of thing. Does it belong or does it not belong? Okay. So a big O is really a set. Okay. When you look at big O of n squared, it is a set of a whole bunch of functions, and each one of those functions is so n squared is a upper bound of all of the functions that are elements of the big O notation, the big O of n squared. Is that okay? We doing okay so far? Yep.
So, if fn is f of n as a function, I'm assuming we have an n squared term in that function.
N squared would be the fastest growing term within f of n. That is correct.
Wouldn't f of n be greater than n squared then? So n squared is actually an underestimate of the time
Nope, because okay, so for that, let's go back to the definition, to the actual mathematical definition. So we go to here, and then we go to upper bound, and that contains the definition. So the definition is f of n is an element of big O of g of n. So in this case, f of n is the complex actual amount of time, and then g of n is just n squared. Okay, so kind of imagine that g of n is just n squared. So we just have to make sure that the ratio between f of n and g of n is not infinity. It has to be less than infinity. So in the case that we are talking about, there's a constant, okay, where f of n divided by g of n is going to approach that particular constant. The larger the n is, the closer we get to that constant. Is that okay? And since we're talking about a constant, it is less than infinity. So it meets this requirement, and as a result, we can now say n squared is the upper bound of f of n. Is that okay?
Yeah.
Okay.
I think in the static case of just n squared, not taking the limit as the function, it probably goes to infinity.
Right.
In a certain case, with a low n value,
Mm-hmm.
f actually bigger than.
It is, but that's fine because as long as that ratio does not approach infinity, we're fine. So so when you look at the big O notation, it does have you have to take into consideration what if n becomes larger and larger and larger and larger. Okay. So after that, after upper bound, so the main point that I want to make is most people, including computer science people, use big O sometimes incorrectly because we use big O as if it is the actual correct, accurate estimate of the time complexity of an algorithm. We have a symbol for that, but it's not big O. Big O is just an upper bound. Okay? It can be a very gross upper bound, but it's just an upper bound. Yep.
So you can literally throw any algorithm into that structure and then I can say, oh, that's O of n to the n, and that'll be correct.
They should have used big theta instead of big O. Yep. So big O is the upper bound, and in between we have some lowercase o, like negligible, and then we have lower bound, which is big omega. So big omega is kind of the opposite. We are basically just looking at the limit inferior of f of n divided by g of n. As long as it is greater than 0, as long as it's not 0, we're good. Okay? So that is basically saying g of n cannot be a gross underestimate of f of n. Is that okay? So it's just a lower bound. So what is a lower bound? If you're looking at the bubble sort algorithm, n is a lower bound. Okay? N is a lower bound of the bubble sort algorithm. So when you look at f of n, you divide it by n itself. That actually approaches, when you take the limit inferior, it actually goes to infinity. But that's okay, because my question is really only asking, is it greater than 0? Well, is infinity greater than 0? Yep, meets that requirement, we're good. So n is actually a lower bound, one of the many, many lower bounds of the time complexity of bubble sort. What about constant time, which is usually represented by 1? That's also a lower bound. It's a very gross lower bound, but it is a lower bound. So omega is a lower bound, big O is an upper bound, okay? So what we really want, or the most important one, is what we call a type bound. So a type bound is a function, g of n, so that f of n is an element of big O of g of n, and at the same time f of n is an element of the omega of g of n. So in this case, the other way to say this is g of n is both a upper bound and a lower bound of the function that we're estimating. So that is what we want. And when people say, oh, the time complexity of some algorithm is blah, 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 what they're really referring to, or what they want to refer to, is big theta. But when they say it, they use the big O notation. They say big O of blah, blah, blah is a certain function. Is that okay? So a lot of times people misuse big O when they meant big theta. Are we good so far? All right. So that's kind of a quick recap of time complexity. So when you look up Wikipedia, okay, if you look up bubble sort, and we'll find it in Wikipedia, it will tell you about the time complexity. So when you look it up, performance, and it says, well, even Wikipedia has it wrong. So it has a worst and average case complexity of big O of n squared. So that is not entirely correct, okay? Because if the actual amount of time is linear, you can still claim that it has a big O of n squared, because n squared is only being said as the upper bound here. And what Wikipedia, or what this page really meant to say, is big theta, because only that is significant. Is that okay? So you can see how the big O term is really not used correctly in many cases. So are we okay so far? Understanding, sometimes when you read, the big O notation, it really is saying big theta. Because, if you substitute big theta in place of big O, then it is actually dead on. Is that okay? All right. All right, so we're going to close this. And of course, we'll write a check to Wikipedia soon. So what we'll do today is moving on to talk about recursive definitions and recursive algorithms. And because you're supposed to be taking cisp430 in the same semester, or have taken it before this semester, most of these really should not come as a big surprise. So the first one is uses the example of factorial. So we look at factorial, and we look at the recursive definition. So the recursive definition is if n is greater than or equal to 1, then n factorial is n times n minus 1 factorial. And then when n equals to 0, then 0 factorial is 1. I should have used n here. When n is as long as n is a natural number, we apply those rules. Okay? So when we try to figure out what is 4 factorial, we can utilize that recursive definition. So because 4 is greater than 0, we can use the recursive definition. So 4 factorial becomes 4 times 3 factorial, which is 4 minus 1 factorial. Then we have to figure out what is 3 factorial. Well, 3 factorial is 3 times 2 factorial, and so on. So we have to keep going like this until we get to 0 factorial. Then we stop, because 0 factorial, by definition, is 1. So we don't have to look any further, because by definition, it is 1. Then we calculate our way back. So 1 times 1 is 1, 2 times 1 is 2, 3 times 2 is 6, and then 4 times 6 is 24. That's why we know 4 factorial is 24. But we are utilizing the recursive definition in this case. So are there any questions about the recursive way of figuring out factorial? Yep.
Didn't you say before that recursion is not efficient? So why are we learning?
Well, it is not efficient, but it is a very interesting. It's an interesting way of looking at things. It makes proofs easier, because you can use proof by induction. Yep.
That's a question actually. Are there algorithms that recursion is more efficient for?
No, unfortunately, because as far as implementation is concerned, every time you have recursion, you are pushing the return address on the stack, and you have to use the return address to resume execution in the caller. So that overhead mechanism, in addition to passing parameters, pushing a bunch of parameters on the stack, and it's always going to be less efficient than the iterative algorithm using an explicit stack. Because when you use an explicit stack, you keep track of your own stack index, and that doesn't have any overhead of pushing the return address and then returning, pushing the return address and then returning, and so on. So the iterative version is always going to be more efficient, but it's going to be a lot more difficult to write the iterative version in some cases. If your recursion only has one single point of recursion, like factorial, then it's really easy. But when you have multiple points of recursion, or multiple points where you can do the recursion, then it gets a little bit harder. So if you look at Fibonacci, the non-recursive version of Fibonacci without using the bottom-up approach is actually very, it's a little bit more intense compared to this. Tower of Hanoi is the same, because when you look at the Tower of Hanoi algorithm, there are 2 points within the algorithm that is recursive. So that makes it kind of difficult to rewrite as an iterative algorithm. It can be done, it is just not easy to express. So this is the factorial subroutine written in a recursive way. So no big surprises there. And then we have, of course, we have to put in Pascal's, triangle, because we have to utilize. Do you guys still remember Pascal's triangle? We spent quite a bit of time to talk about Pascal's identity and then the binomial theorem. Okay, so using that, we basically say, if you want to figure out the value of row R and column C, if it is column 1, which is the leftmost column, or if the column number equals to the row number, then the answer is 1. So that handles the entire left edge and also everything to the right edge. What about stuff in between? Well, stuff in between, we can use the recursive version of that, okay? So we try to figure out what is the Pascal triangle value of the one row before and then the one column before. And then what is the value of the cell that is only one row before but the same column. Once we figure out those two numbers, add it, and that becomes the Pascal's value of inside of the Pascal triangle for row number R and column number C. Is that okay? All right. So that's recursive. And this one also has 2 points of recursion. So it's harder to write it without using recursion. And here's Tower of Hanoi. How many people have coded Tower of Hanoi before? Okay. So when you coded this, did you just, print messages like, I'm moving a disk of this size from this pole to this pole? Okay. If you go online, there are really nice rendering of actual disks being moved. Okay. So you can take a look at that. So Tower of Hanoi animation. And this one, it works on 5 disks.
Introducing the new
There we go. And by the way, how many moves do you think 5 disks is going to take? Do you remember the time complexity relative to the number of disks? It's 2 to the power of. So it's going to take a while. All right, so it's a little bit boring, a little dry. It's not like the Hungarian dance, sorting algorithm thing, or the Tango for binary search. Yeah, not very exciting. But what is the principle? How does the algorithm work? And what is the original problem? Okay, what problem are we trying to solve here? So 2 to the power 5 is only, 32? So it's not too bad. But what exactly is the problem of Tower of Hanoi? I mean, you guys can search, online for that. So you're given 3 poles, okay? We'll just name the poles, A, B, and C, okay? So the objective is you have a stack of disks on pole A, okay? And the idea is you cannot put a bigger plate on top of a smaller plate. That is the only rule. And you can only move one plate at a time. So the question is, how do you move all the disks from pole A to pole C? That's the question, okay? And I think the original challenge involves, 64 disks or some really crazy number of disks, okay? Because if you think about, the number of moves you need is 2 to the power of 64. That's a really, really big number, okay? So, but what is the general approach? The general approach is you just say, well, I will change this problem to a smaller problem. What kind of a smaller problem are we talking about? Instead of moving every single disk from pole A to pole C, I'm going to change it to a smaller problem. I'm just going to move all except for one disk from pole A to pole B. Okay? So let's say that's doable. You get that job done. Okay? You move everything except for the largest disk at the bottom of pole A to pole B. Then you say, okay, now I can just move the largest plate from pole A all the way to pole C, which is where I want it to be, right? Then you have a smaller problem again, which is to move all the disks from pole B to pole A. Do you see how that problem is breaking up into 2 quote-unquote smaller problems? So what do we do with that n minus 1 disks on pole B? How do we move those to pole C? Well, use pole A as a temporary post, and then repeat the whole process. So that's the whole idea of the solution of Tower of Hanoi. So that's why it has 3 parameters. It has 1 parameter, which is the number of disks, from which pole we are moving those, to which pole are we moving, and which pole is basically the intermediate pole that you can use. And then when you look at the algorithm, let's see. So we know this is the base case. The base case is when you have one single disk to move, then you just say, oh, we don't need the via anymore. We just say, oh, whatever the disk is, we move it from the from pole to the to pole, we're done. Does that make sense? When you only have one pole, you don't have a sub-problem to solve. Okay? What if there are more than 1 poles? Then you use the recursive one. So now we have the recursive version. When n equals to 1, easy peasy, no need to do recursion. But when you have more than 1 poles, then we involve the same algorithm, Hanoi. This time we have n minus 1 poles. We are moving those disks, n minus 1 of them, from the from pole, which is the same as mine. But this time I'm moving those disks with a destination of via, okay, through the to pole. So that's the same thing as moving n minus 1 disks from pole A to pole B, okay? Then with the largest disk left on pole A, I can now move just that one single disk from the from pole to the to pole. The via is not even used anymore because there's only 1 disk involved. After that, I get into the subproblem again, because now I have to move those n minus 1 disks from the via pole to my actual destination to pole using the from pole as a temporary pole. And that's how we solve the problem of Tower of Hanoi. Is that okay? So if it looks kind of simple like this, how come the time complexity is so bad? Each time it breaks into 2 subproblems, right? But how big is each subproblem? Each subproblem,
Based off the fact that you have so many poles and you have to move those poles multiple times, so you based off that.
yep. And that's why each time when you do the recursion, it splits into 2 subproblems, but each time the subproblem has to split into 2, and the number of levels you have to do that split is the number of disks. So that's why when you look at the overall time complexity, it is 2 to the power of the number of disks, which is pretty bad. Okay. And then we look into how to delete a directory. Now, most of you do not have to deal with this because you just right-click on a file, or you just click on the file, and then you press the delete key, or you drag it to a trash can. So you never really have to understand the recursive part of it. But when you try to do something by hand using the command line, and you're doing it folder by folder, or file by file, then you will understand that you cannot delete a folder unless it is empty. So the only kind of folder you can delete is an empty folder. So what if a folder has subfolders, and each one of those subfolders has another folder, and then it has to go down like 7 or 8 levels before you get to folders that only contain files? Then you have to do it recursively. Okay, so the recursive algorithm is going to be something like this. Okay, when you want to nuke a subfolder, then you basically, okay, let me see if I can change the font size a little bit so we can see the entire code. So when you want to delete or nuke a whole folder, then you have to ask, is the folder null? If the folder is null and the error number is not a folder, that means it is a file. Okay, we can delete that, not a problem. We don't have to do it recursively because what you're telling me to delete is not even a folder. I can do that. Okay. What if Peter is non-null? So that means it is a folder. Well, if the file that you asked me to delete is a folder, then we have to do it in a recursive manner. What kind of recursive manner are we talking about? Well, we first change into that folder because we are looking at the folder from the parent folder perspective. And then for each entry within that folder, we are calling nukedir again. So that's recursive. Once you nuke everything within that subfolder, then we can delete that folder, rmdir. And so as a result, we have recursion this time in a loop. So how many times you have to do recursion within a level of invocation is not even constant anymore. Tau of Hanoi is constant, two recursion calls within the same level. Okay? Factorial only has one recursive call per level. This one is not even a constant. It all depends on how many subfolders are we talking about. Some folders have 6 subfolders, other folders have only 3 subfolders, some folders have no subfolders. So that's why this one is even more kind of nasty when from the perspective of turning it into a non-recursive one. Yep.
So basically, when I'm deleting a huge folder,
Mm-hmm.
many subfolders, about like 1,000.
Mm-hmm.
So the time for being this folder, like parent folder, to be deleted, basically it's not a physical deletion. It's a calculating how many subfolders in it, right?
You have to perform that operation to each of the subfolder.
Yeah.
Yep. Mm-hmm. But we know the time complexity. The time complexity is basically the number of files and folders in total that you have to delete, because everything only has to be visited up to twice. So it's not too bad, okay? If you combine all the folders and subfolders and files and they turn out to be like n, okay, then the time complexity of this particular algorithm is really just n, okay? Now, let's turn this around and look at it as a graph. What? A folder structure as a graph? Does that make sense? How do we look at that as a graph? If you look at a folder and you consider, has a, okay, the relationship has a member as an edge, then it becomes a graph, right? Parent folder has all of these subfolders. Each subfolder has all of these subfolders. Each of these folders has subfolders, has individual files and so on. So has becomes a edge, okay? So now we can look at a folder structure as a graph. Now it is not a general graph either. It is guaranteed to be a tree because a file cannot belong to 2 different folders. So this is guaranteed a tree, but a tree really is a graph. So in this particular case, looking at it as a graph, what is the time complexity of something like this? If I want to delete everything within the folder structure, what is the time complexity? In other words, is the time proportional to the number of vertices, or is it proportional to the number of edges, or is it proportional to the number of edges squared? What do you think it's going to be? It's going to be the number of edges, which is actually about the same as the number of vertices, because it's a tree. Okay? Now, trees are very special because the number of vertices is very close to the number of edges. They're only off by like a little bit. Okay, so for estimation purposes, you can use either. All right. What is the next one? When should you consider using recursion? When cursing once is not enough, right? We have to recurse, curse again. So when do you want to consider recursion? I mean, there will be times, especially, not especially, but these days, there will be times when you need to consider algorithms, and sometimes there may not be any existing algorithms that can do what you want to do. So when do you want to consider recursion?
When the same test should be repeated many times.
Okay, that's one way to put it. Let me.
You can break the problem into a subproblem that's similar to the original one.
they have the same nature, right? Yep. Go ahead.
When the language doesn't have iterations.
When the language does not have iterations, okay. Well, when the language doesn't have iterations, then you have to use recursion. That is correct. But at the same time, you can take any recursive algorithm and turn it into iterative algorithms. So it's more of a way of looking at the problem than it is, a language issue or it is a programming technique. It is how you look at things. Okay. All right. So what we'll do now is to look at things that we normally see as it is not recursive, but we can actually do it in a recursive way. So I'll give you some examples. I don't think those are in the notes here. Yeah, they're not in here. So I'll give you some examples of how to turn something that is non-recursive into recursive. But it fits the requirement. It doesn't feel like we are shoehorning something that is naturally iterative into recursion. Okay. Okay. So we'll take a look at a few examples. The first one we'll look at is string copy, or string and copy if you prefer. Okay. So we are looking at string and copy. Does everyone know what is string copy or string and copy? Does anyone not know what it is? Nope. Okay. Yeah, if you don't know what string and copy is, you can just look it up because it's a pretty well-known string function in C and C++. And if you look up, C++.com, which is probably the most definitive source of this sort of thing, all it does is to copy a string. It has 3 parameters. It copies a string from source to destination, but only up to num bytes. So it is limited by num. So this way you can avoid problems that usually leads to stack overflow, exploits, and whatnot. Okay. All right. So you look at this, something like this and go like, that is clearly iterative. Why is that? I cannot see how this can be done recursively. Well, let's take a look. So we'll copy the prototype from here. So char pointer str and cpy, char destination, const char source, and then we have size t, which is basically just unsigned integer as num. Okay. So we look at this and go like, we know exactly how to do it as a loop, but how do we look at this as recursion, as a recursive algorithm? The first thing is do it in the lazy way. Okay. You think, okay, when do I stop? When do I have nothing to do? When num is 0, I got nothing to do. Very good. Okay. So if num is 0, then it's good news because I have nothing to do. Absolutely nothing except to return, I think it returns destination. Okay. And this is how you can chain a whole bunch of string functions together, because the return value of one string function is the same string that gets the result of the operation. So you can basically nest the calling of string functions in a big thing, and make your code really hard to read. Okay. All right. So that's one. Okay. So the else case is basically saying, what if num is non-zero? Okay, but I'm still lazy. I'm still looking for an easy way out, right? So I'm going to say, well, in that case, if whatever source is pointing to is my null character, I'm done. Because in that case, I just have to copy that, right? So destination, whatever destination points to gets whatever source is pointing to, and I'm done. And I'm going to put this return dest at the very end because that's just what I need to do. Okay, there you go. Is that okay? Because I know I have at least one more character that I can copy. There's more space. But what I'm seeing in source, which is where I'm copying from, is an empty string. It just has a null terminator. Does it make sense that I just have to copy that null terminator and I'm done? There's nothing else to do. Cool. Okay. So what about the else of this part here? In other words, num is non-zero. I got additional space, But source is non-zero either, or what source is pointing to is not a null character. So the string is not empty. I got at least one more character that I have to copy. I have to do some work. Okay. So you can basically put this on the outside of the conditional statement because regardless, you have at least one character to copy. So we'll move this outside of the conditional statement, in which case there's nothing to do when it is 0. But I'll keep the structure like this, because I don't feel like changing it. So, I mean, your compiler is smart enough not to actually produce any code that is inefficient. It's just, it looks strange, okay? So when I get to line 15, what does it mean? Well, it means I got, there's something else that I might need to do, okay? But I don't feel like doing it. Maybe the next person, hey, you can do it. So when I pass my subproblem to you, it's not going to be the same problem that I have anymore. So from your perspective, the source is not the source that I'm looking at. The destination is not the destination that I'm looking at. The number of bytes available is not the number of bytes that was available to me. Everything is now off by 1. You have 1 fewer characters to play with. And then the source is 1 byte past what I have just copied. And then the destination is also going to be 1 byte past what I have copied into already. So now the problem is really just this. Okay, so we are now saying, let's do another string copy recursively. But destination is now destination plus 1 because, I just used up that byte on line 9. Okay, so that byte cannot be used anymore. Source is going to be source plus 1 because I just copied that byte from the source. And then num is num minus 1 because there are now 1 fewer bytes available to the next person who has the rest of the string to deal with. Well, there you go. Recursive version of string and copy. Yep. You should return what? Well, they're all going to get down to here, so they're all going to return destination. I'm just tossing that away because I have no use of the return value of the recursive call. I don't want to return this though, because this is going to return dest plus 1. So I'm going to toss it away because it's of no use to me. So is that okay? Turning something that normally is not recursive into recursive? But it does make sense, right? It does make sense because you're dealing with a smaller portion of the string that was given to you. You're passing this subproblem to someone else, but that problem is now smaller. But do we want to implement string and copy like this in the C library? Probably not. Okay? Why not? Because it is extremely inefficient. Huh? It takes, well, the amount of time is not even the key issue. It's the amount of space it's going to use up on the stack that is going to be the issue. If you have not taken assembly language programming, then you may not understand this part. But all the arguments are on the stack, along with 2 more things at least when you're talking about a commercial processor. So we are talking about this is on the stack, this is on the stack, this is on the stack, along with the return address is also on the stack. And then with a modern processor like the i386 processor, the frame pointer is also going to be on the stack. So we know for sure with a 64-bit processor, it's going to use up 40 bytes, okay, or 5 times 8 bytes, okay, for each invocation. But we're only copying 1 byte per invocation. Okay, so if you have 1,000 bytes to copy, it's going to chew up 40,000 bytes on the stack. Okay, that's pretty inefficient. Okay, so that's why we don't implement it this way. Okay, in C and C++, because it is awfully inefficient. But it doesn't mean that in theory we cannot look at it in a recursive way. Okay, which is what we are looking at here. So are we doing okay so far with this example? What about linear search? Do you think we can turn linear search into a recursive algorithm? Yeah, easily. So you take an array, okay? Okay, this is This is how we do it. So this is not binary search, by the way. Okay, this is linear search that works on arrays that are not sorted. Okay, so we'll say this is linear search, and then we have, let's say we are just dealing with an array of integers. Okay, the idea is the most important part. So we have const int. This is the array. And of course, in C and C++, you have to pass the number of elements in the array. So that's going to be passed separately. And then we have k, which is what we are looking for. Okay. So linear search returns true if k is found in the array, and it's going to return a 0 when it is not found. Okay. So you go like, well, we know how to do this in a while loop. That's a pretty easy thing to do. You just have a temporary variable I. It goes from 0 and then work its way all the way to n minus 1. But if you find an array element, array bracket I, that matches the value of k, then you exit right away and then you return true. Okay? That's the typical way of doing it. But if you want to do this in a recursive way, how are you going to do it? We can use the same approach as the previous one. Okay? So we can say if n equals to 0, returns false. Well, because if your array is empty, it's guaranteed not to have an element that matches the value of k. Okay, what if n is non-zero? Well, if n is non-zero, then I'm so lazy, I just look at the first one. Okay, I'm just going to say if array bracket 0, which is the first element of the entire array, equals to k, because I'm guaranteed it has at least that much for me to compare, right? Then I'm go like return true. Cool. Or in the case of C and C++, the best way to specify a value of true in C and C++, in my humble opinion, is to say it is not false. Okay, it's a joke. Fine. Because we don't know exactly what value we should be using, right? Because anything that is non-zero as an integer is considered true. So as a programmer, are you going to use 2 to represent true because it starts with t? Or are you going to choose 1 because it's the next available integer next to false? Or are you going to pick -1 because it's all ones when you look at it in a binary way? They all seem to be so legitimate. It's difficult to pick. So the idea is don't pick. Just say it is not false. Let the compiler choose for you. All right, but that's just a joke. So what if that is not the case? Bad luck. What I'm looking at is not what I want. But it's not my problem anymore. I'm just going to pass that problem on to somebody else. So I'm going to say, well, I can't find it, but maybe you can. So the array that you have to deal with is array plus 1. In other words, your starting point is 1 past my starting point. And of course, you don't have as many elements anymore. You only have n minus 1 elements to search through. But k is still the same because we are still looking for the same value. So let's see. Yeah, that would do it. This is really bad programming style because I'm using return inside a nested conditional statement. So it's really poor programming style from that perspective. But nonetheless, I just turned linear search from iterative into recursive. But you can see it is a perspective, right? We are changing the perspective of asking, when can I stop? Oh, I see I cannot stop here. So if I cannot stop, can I present the rest of the problem that I need to solve as a subproblem that has the same nature as the problem that I was supposed to solve? Because if I can do that, then I can call the same subroutine again, but this time to solve a smaller problem. Yep.
Do you even need the return statement at the bottom? Because you've already returned 0 and you've returned true if you found it.
Which line are we talking about?
35.
On line 35.
I wonder why we even need a return statement because you're just calling the same function again.
Because even though we are calling the same function, that function will return to this place. So if I do not have a return here, lean search is going to come back to this place, and then I need to specify a particular value to return. That is the projector timing out. Oh, no, it's my cable. And this, did it change the, yep, it changed the resolution again. It does that automatically. So I now need a bungee cord or duct tape. There we go. Or just kind of push this in a little bit so I don't accidentally pull that cable out. There we go. So are we good so far with this? Yes? Okay. But do you see how it is in a way easier to figure out compared to the iterative version? Maybe not. I don't know, because I can see it both ways, the iterative version versus the recursive version. The recursive version is interesting because you're looking at it from the perspective of I'm trying to be as lazy as possible. How can I do the least amount of work? Okay. When there's nothing else left in the array, the answer is easy. Okay. Darn it, if there's at least one thing, I'll just do the comparison to that one thing guaranteed to be in the array. If it doesn't match, then I will turn it into some problem and say somebody has to deal with it. Is that okay? So it's a perspective. How did you come up with an algorithm that is iterative for linear search? Can you remember? If you kind of go back in your memory lane to CISP 300 or 360, and your homework assignment or your professor tells you, okay, let's work on the linear search algorithm. How did you figure out the condition of that loop? The number of elements. So you know that that's basically a boundary. You cannot exceed that. Okay. But how do you know that you should also exit when you find an element that matches the value? Okay. So that becomes the question, right? Is it easier to look at things this way, or is it easier to look at it from the perspective of a loop? This doesn't have to have a loop. It doesn't even think of things in a repetition way using a loop. It is looking at things from a perspective of, oh, here's a smaller problem, and this is the nature of the smaller problem. Okay? So I'll let you guys kind of ponder, when is a good time to use recursion, because it has its place. Okay, recursive algorithms definitely has its place. Well, we got enough time, so I'm going to give you this problem as well. Remember A star? I hope so, because that was only 2 classes ago. So let's say that we have a problem where the graph is complex enough that you may not have enough time to finish A star by the time you have to make a decision of where to go next. Okay, that can happen with robotics. Okay, it also depends on what each vertex is representing. So it can happen. So let's say it's a robotic arm trying to grab something, or trying to decide what to do with something that is dropping through a particular place. Okay. So in that case, you definitely you only have so much time because it's physically limited. So now you have what we call a hard real-time problem. Hard real-time problem means if you cannot make a decision within that amount of time, it is considered a failure. So you have to make a decision within a certain amount of time. So let's just say that your graph that you have to search through to find the shortest path is complex enough that you may not have enough time to finish A star. Now, using the traditional A star algorithm, if you cannot finish it, it doesn't really give you an idea of which edge you should take from the source or the original vertex. So now you don't have an answer at all. Okay, you just say A star is not done. I don't know what to do. So now it is considered a failure. So what can we do in these cases and go like, I'll give it the best shot. Okay, I know this may not be optimal because I didn't have time to finish the A star algorithm, but I'll just give it a shot. So how would you do that? Now remember, this is A star algorithm, which means there is the component of a heuristic. So an heuristic is also a way to guide the algorithm toward the shortest path. Okay.
Basically,
Yep.
basically you get to the point when you have time, and then when you're out of time, you just add in the next heuristic.
Yep. But what do you why do you think it has to do with recursion? Yep.
Because your next step will use a smaller problem next. Because when you make that choice, you then lose a little bit of that problem too.
It's actually not that. Okay. But that was a good guess. Okay. It has to do with recursion because the alternative algorithm to deal with situations that I just mentioned is called a C star algorithm. I think it's called a C star algorithm. Or it's the recursive iterative version of A star. Let me look for that. Recursive iterative A star. They don't have it. Okay. That's okay. So what you do is you set a maximum search depth. So you start with 1. You basically go, okay, I know I don't have a whole lot of time, so I'm just going to set my maximum search depth to 1, which basically means from your start vertex, you just say, I'm just going to look at all the outgoing vertices, and I combine the cost of that edge with the heuristic of the outgoing vertex to the destination, and I'm going to use it as a really, really rough estimate of the length of the shortest path if I choose to go this way. Okay? And you do it to every single outgoing vertex, and then you just say, okay, based on this, this is the best option. And then you look at the watch and go like, oh, I got time left. Let me increase the depth to 2. So now you do a depth first search with a maximum depth of 2. So you go boom, boom, okay? So now you're looking at 2 vertices away from the start vertex. You add up the cost, the actual cost of those 2 edges, and then you add the sum of that to the heuristic of the second level vertex to the destination. And you do it to every single one, and then you just pick the best option, okay? So that estimate is now slightly better than the first one, right? Because you have a slightly better accuracy because you actually explored up to 2 edges down from the start vertex. Then you look at the watch, go like, I got time for 3, to do some more processing. So now extend it to 3, 4, 5, and so on. So let's say, somewhere within, the depth first search up to 7 levels, you ran out of time. Okay, the timer came up and go like, okay, we got to make a decision now. So you go back to the previous one where you have explored up to 6 edges down, and you just say, well, based on that particular search, this one is the best option. You just take that option. Is that going to be the best option? Probably not, but that's the best you can do given the amount of time you have in order to make a decision. Okay, so that's kind of it's a very niche type of algorithm because it is not applicable to places where, oh, I got all eternity to figure out the right answer, so I'm just going to wait until the perfect answer is there. Okay, we would like to have that. Okay, but sometimes you can't do that. Okay, you're solving a real-time problem, it's a robotics kind of problem, and you just don't have the luxury to find the best answer. You just need to find, given the amount of time, what is the best answer at that time. Is that okay? So that actually is a particular algorithm. I just cannot find the correct name of that. So if I can find it, I can. Oh, iterative deepening A star. There we go. So that's the official name of what I just described. I don't remember why it is called a C star as well. I guess there's a B star. Maybe there's a D. There's a D star, except there's not a C star. Darn it. So interesting algorithms, okay? Because these are when I was in graduate school, this is the kind of AI stuff that I was interested in. not neural nets, not trying to make computers, do things the same way that we do. Why would I want that? Okay, nobody's getting that. See? So if I ask that question, nobody's getting that. Do I want my computer, my AI computer to come up with the same answer? Like, I have no idea what you're talking about. Or do I want my AI algorithm to actually try to figure out, okay, let me see what you actually mean. This is a little digression, but I think it is important because you guys will see more and more and more deep neural net applications in the realm of AI to do things that people can currently do. Okay? And the interesting observation is deep neural nets, they learn for sure. Okay? So it is a form of machine learning. But what they learn is based on what they're exposed to. In other words, they are trained. You present a problem, you present, what is done, and then you present a weighing factor, like how successful this method was given this problem, this scenario. And you give it like a bazillion training samples like that. And the hope is with a multi-level deep neural net, it will figure out the structure or the correlation between the problem, what you can do, and which action gives you the best result. But does it reason it out? Nope, there's no reasoning when you're talking about deep neural net. All it's doing is trying to look for a hidden pattern that we normally cannot see. So it's doing some form of abstraction, but it's not a logical analysis type of abstraction. It is basically just numbers, and it will try to figure that out. So if you present problems, this is how people do it, and this is the end result of that particular way of how people do it, then the deep neural net is only going to learn what we have considered doing. And it will respond in a way, this is a projection, okay? So it will only respond in a way where it is limited still by what we can consider as potential actions to take. So if we as human beings, all have a blind spot and there are many options that we do not even consider, then it has none of those training samples anymore, right? Then it cannot learn to perform those actions because it was never exposed to, oh, I could have done it this way and it would have given me this result. And that's why when they talk about AI having like bias, like people do, it's not surprising. Okay, why would we be surprised when we are using human data to train a neural net, and the neural net ended up having the same bias that people do? I am not a single bit surprised by that. So that's kind of interesting. And Watson is not neural net based. The IBM Watson AI engine is not neural net based. So that's kind of noteworthy because everything else these days are a lot of stuff is neural net based. How many people are thinking about going into AI? One, okay. I think that's going to be it's going to be a very important growing area. When you start to integrate AI with computer security, I think that's when we will start to see something that's truly disruptive, where two separate branches of technology or fields of study that normally do not interact with each other start to we start to combine those two. That's when we start to see things that we normally would not expect to see. So you have AIs figuring out how to hack into computers, and then AIs to detect that something is being hacked and try to counter that. That's going to be automated. I can guarantee you that, because finding security flaws to exploit is a very tedious process. So there will be a lot of money behind the drive to automate that process. And that process, interestingly, has a lot of elements that we talk about in this class, because you are looking for a flaw within a program. So how do you find a flaw in the program? You just bombard it with all kinds of invalid data and observe what the program is responding to it. You're looking for something unexpected. Oh, it didn't catch this problem, or it didn't respond the way that it's supposed to. Now you might have something that you can exploit. And that can be automated. So there you go. There will be jobs that we cannot even think of today. So are there any questions about all the topics that we have talked about? I don't think I can, introduce anything beyond this particular point. So all of this stuff here is really just, recursive applications and analyzing a little bit of how much time it takes. And when I talk about context, that is basically a context is what we call an invocation in subroutines. Okay. So are there any general questions about recursion or the recursive way of looking at things? Why do you think this is not a big topic in a normal math class? I mean, your calculus class doesn't talk about recursion, does it? Your algebra class doesn't talk about recursion. So why is it that we talk about recursion in this class? What is different about, how should I put it? What is the difference between the objective of this class as opposed to a calculus class or even algebra? I mean, this is a computer science class, okay? It doesn't seem like it, okay? There's no programming or very little programming in it. But what you're learning, the concepts that you're learning, is still related to programming, okay? So in programming, do you see in your future that you might actually need to use recursive algorithms? There you go. And then it also has to do with discrete, okay? Because calculus is continuous. When things are continuous, then there's no next level because everything is continuous. There's an infinite number of points between any 2 points. But when you are talking about discrete math, which means, okay, here's 1, here's 2, here's 3, and so on, there is the distinction thing of this is where I am, this is the next whatever. And that is required in order for the concept of recursion and proof by induction to work. Is there's n, and then there's n plus 1. Calculus doesn't have that. Algebra does not have that. But discrete math that we are dealing with in this class, like sequences, does have that. Okay? So all of those things are kind of tied in together. What you learn in this class may not be applicable by itself, but it will be at least useful in other classes that you'll be taking at a 4-year university, like the analysis of algorithms. There will be a lot of math in that class. And hopefully this class gives you some of the tools that you need to take that class. Have you guys looked into what kind of classes you have to take to get your 4-year degree? Do you guys remember a class called the analysis of algorithms? Yep. So that's the next heavy duty math class in computer science. Some of you will probably look forward to it, and some of you may not like it. All right, well, we are out of time today. I will see you guys next Monday for the practice test. So I would study a little bit over the weekend, go over the material, and see if you have any questions about the material that we have already gone over after the first exam.
Professor, I have a question.
Yep.
I'm enrolled in your cisp440 for next semester.
Mm-hmm.
And